Hello everyone. Thank you for your interest in our work, event-based visible and infrared fusion via multitask collaboration. Visible and infrared fusion is a technique that combines data from two types of sensors into a single image, the visible sensor and the long-wave infrared sensor. This fusion enhances the imaging systems by enabling perception across multiple spectrums. The visible sensor captures detailed, texture-rich images, while the infrared sensor detects thermal signatures. Integrating VIS and IR provides a comprehensive view, merging the strengths of both sensors to offer complementary information. This technology is crucial for applications such as surveillance and autonomous driving, enhancing both performance and safety. Current visible and infrared fusion systems usually use frame-based visible sensors with several limitations. First, they have a limited dynamic range, typically less than 70 dB, which can hinder detail perception in high-contrast scenes. Second, their frame rates are restricted, which may cause motion blur. As a result, their frame quality is often low in complex environments. To overcome these challenges, we propose to use an event camera as the visible sensor and develop an event-based VIF system, or EVIF for short. Event cameras have multiple advantages that can enhance the VIF systems. These cameras have high dynamic range and high temporal resolution, which can provide high-quality visible textures. Furthermore, the motion details in the event signals can also offer crucial clues for deblurring IR images. Therefore, EVIF can obtain enhanced imaging quality for both visible and infrared modalities, achieving robust fusion results. To effectively fuse events with infrared frames, our core idea is to dissect EVGF into three subtasks: event-based visible texture reconstruction, event-guided infrared image deblurring, and visible and infrared fusion. Instead of learning these three tasks separately, we adopt a multitask collaborative framework, which leverages features from one task to facilitate the learning of others. The whole framework is shown in the bottom figure. Specifically, we first develop a cross-task event enhancement method to inject useful texture details from the event reconstruction task into the infrared deblurring task, enhancing the IR deblurring performance. This is done by processing the event features from the reconstruction task through bidirection GRU and fusing the processed features through a cross-task channel attention module. Next, we develop a bi-level mutual information optimization method to highlight complemented features from both visible and infrared modalities and obtain robust fused images. This is achieved by enforcing mutual information minimization between filtered modality features and maximizing the mutual information between fused features and original modality features to avoid information loss. We conducted extensive experiments to evaluate the performance of our EVGF system using both synthetic data and real data captured by our prototype hardware system, as shown in the bottom right figure. Experiments on synthetic data show that EVIF can generate fused images with no obvious motion blur or exposure issues, while conventional VIF methods tend to generate blurry and overexposed results. Our captured real data show that real-world scenes are even more complex and often exhibit significant motion and high dynamic range. The results on real data demonstrate that EVIF can effectively handle these extreme conditions compared to conventional VIF systems, ensuring clearer and more reliable fusion results. We also conduct a series of ablation experiments to investigate the effectiveness of our proposed cross-task event enhancement and bi-level MI optimization. The experiment results show that both methods work effectively, which can enhance the IR deblurring task and promote fusion quality. Finally, it should be noted that in static areas with no light changes, there will be no event signals and EVIF will not work properly. This is one of the limitations of EVGF. An example is shown in the figure, where we demonstrate a car carrying cameras is stopped at a red light, with only moving pedestrians being captured by the event camera. In such a condition, the static background visible information is lost by EVGF. Therefore, EVIF is complementary rather than competitive with existing VIF systems. That is all. Thanks for your attention.